mode.
And I'm going to unmute Michael right now.
Great.
Hello, Michael. How are you, sir?
I am well, Don. How about yourself?
Well, I'm fine. This is Rob. Don is here in the wings, just waiting for his cue to join. And I think you and I talked the other day, as a matter of fact.
Yes.
You're with Lord Corporation, yes?
Yes, I am.
Yes, very good. Nice to speak
I
with you.
didn't realize it was you instead of Don.
It's both of us today. I am what Don would refer to as his Roz, if you're familiar with the Fraser show.
Okay.
So I'm just moderating today, and if anything break out, I'm just supposed to step in the middle. That's all.
Sounds good. Am I the only one in so far?
Yes, sir, you are. As a matter of fact, I wanted to let you know that you're, and I'm trying to remember if it was one or two individuals, Michael, that you had gotten into the webinar, the fundamentals webinar. Yep.
Mike Gordeev and Francis Rainey.
Exactly. We had the pleasure of meeting them over the past few days, and I think it's going rather well. And with that, Don, I will leave it to you to take from here.
Okay, great. Well, hi, Michael.
Well, hello, Don.
Have you had any feedback from the webinar?
Yes, I have. I spoke with Mike this morning about the second day. I had followed up with him also on the first day on Tuesday, and they are both really enjoying it. They love your style. Mike made the comment that getting people to participate seems to be a challenge. And so he says after a while you just got to ask just so that you know that someone else is really on the other side of the conversation.
That's right. I can't see them, and that's frustrating.
Exactly. But he said that he reiterated a comment I think he made on Tuesday that the information is dense, and that's not a criticism. I think people don't fully appreciate. People who don't use GD&T don't fully appreciate how much is really involved. You know, they feel like tolerancing is as simple as just put a plus or minus tolerance on the dimensions. What more could you ask? And
that's right.
You know, you get into it and you realize, wait a minute, it's a whole lot more that you need to ask.
Mm-hmm. Yeah, we struggle, especially with, I hate to say it, but with young engineers, and it's not their fault, but the colleges, for the most part, are not teaching geometric tolerancing, and then they come out of college and they're expected to sign off on drawings and determine some tolerances or do analysis, and they really don't know what the variation is.
And you're absolutely right. First of all, I'm late in my career. I graduated in 1980, and I didn't even hear about GD&T until probably 82 or 83, and ended up taking it in a 2-day course in the 80s, and then quite honestly have been working at it ever since, which is to say, you know, understanding really everything that's there. So it really is. I'd never seen any of it in school, and you know, I see young engineers coming out, and you're absolutely right. That's not where they get it. They all get it in industry once they get out.
Right. Sounds like maybe someone else has joined us.
Hello, Kevin. Are you there? Nathan?
Yeah, this is me. Can you hear me?
How are you today?
Fantastic. Yes, we can. Thank you. We can hear you both. And Kevin, I think we're getting a little bit of an echo back from you in your room.
Yeah, that's okay. I can, you can mute me at any time.
No worries. And I'll tell you what, I will leave that up to you, Kevin. I have the ability to do that, but should you like to do that yourself, you're welcome to, and that way you can open it up whenever you have a question or such.
Certainly. Thank you.
You're quite welcome. And Don is on the line with us. So we have a few individuals, and Don, you're ready to go whenever you'd like, or we can wait to see if anyone else joins.
Well, why don't we just do a little bit of introduction here. So we have Michael, we have Kevin, and who else did you say had joined us?
Nathan.
Nathan. Okay. So maybe if each of you could just share what your job function is and a little bit of your background in geometric tolerancing. Michael had already shared that he had his first class back in the 80s. And Michael, what do you do on the job?
I'm a design engineer. I've been working as a design engineer pretty much my whole career, and we make here at Lord Corporation, we design anti-vibration control systems, or in this group, anti-vibration control systems for the aerospace industry. And then it's an electromechanical systems group, and then we have other electromechanical devices that we apply both in aviation and industry, or just commercial applications.
Great. Okay. And Kevin?
Morning. Good morning or good afternoon, depends on where you're at, I suppose. We're in south central Minnesota.
Yes.
We're I'm with AGCO Corporation. Can you hear me?
I can.
All right. I'm with AGCO Corporation. We design, build, and construct Massey Ferguson tractors, agricultural sprayers. We build lots of big stuff. I'm a quality technician. I do most of the inspection. We're dealing with castings, molded plastic parts, sheet steel, bent steel, glass, cabs, seats, everything that goes into a tractor. And I've been hosting and teaching a GD&T class here using all your materials, and it seems to be working out wonderfully.
Oh, super. Glad to hear that. And so, Kevin, whenever somebody's using our materials, I leave the door open. You can email me anytime if there's a question about something, you wonder how I might say it, or where I was trying to go with a particular slide, and I'll be happy to get back to you. And then Nathan.
Yeah, hi, this is Nate Weister from Eden. I'm a designer, and we make circuit breakers, all sizes.
Okay. Well, welcome everybody, and I know that there's a lot of people that tune in. They might not make it today, but they'll watch the video. So just remind you, this is being recorded, and if you miss part of it, you can always go back and review it on the premium site. I'm always struggling for what topics to have in these brown bag sessions, so I'll probably say it at the end also, but I encourage you to send in any suggestions you might have. We've tried to make the brown bags a little different than the fundamentals or applications course, although some of what you're going to see here does come out of our new applications course. But it's topics many times that there just isn't time for in the seminar. And I thought today I'd just talk for a while about having the right geometry. I find that many times designs don't have the best approach in their geometric shapes. And so I'm going to take you through a few case studies and talk a bit about that. Whenever I think about having the right geometry, I think about those things that I buy that come in a flat box and they have those lies on the outside. You might be familiar with those. The lie number one is usually some assembly required. And when I see that, I know there's going to be a whole lot of assembly. And then it'll often say tools required, something like a screwdriver and a pair of pliers. And that's fine, but they fail to mention that you're also going to need a hammer and a drill and maybe a bigger hammer and drift pin and maybe a bigger drill and, I don't know, a cement mixer. They leave out some of the tools you may need to put it together. And then they say approximate assembly time, 30 minutes. I can remember being suckered in on that with a kitchen set one Christmas Eve for my daughter. I started putting it together at about 11:30 at night, thinking midnight, I'm in bed, being an engineer and all. Well, the next morning, after spending several hours through the night, I had to say, oh, honey, look, Santa didn't have time to finish putting it together, so Daddy will have to do it today. I firmly believe that the people who print this information and design these things have never thought about having the right geometry. If you've ever dealt with putting together a gas grill, any sort of exercise equipment, you know what I'm talking about. Then there's an instruction when you open up the manual, and the instruction says, do not tighten any fastener until fully assembled. The trouble is, many times, once it's fully assembled, you can't get at a lot of the fasteners to tighten them. I just went through this with a workbench. It had a drawer, and the track for the drawer was bolted onto the sides of the workbench. And the instructions said to close the drawer and line it up so you had a nice uniform gap all the way around the door, and then tighten the screws for the track. Well, when the drawer is closed, so you can get that nice alignment, you cannot get to the nuts that go on the ends of the screws. So you may have experienced something like that. And I just want to say that there's been a lot of emphasis over the years on using maximum material condition on things like holes that are for assembly. And that's good. It makes it, better for production. But oftentimes, in order to put everything together, you have to follow this instruction. You have to leave things loose and float them around to get everything to locate. Now, from your fundamentals training, I hope everybody knows that all parts in space have 6 degrees of freedom, whether we're talking about an airplane or some machine part or molded part. We have the 3 translations, or also I'd say they're the 3 tudes, the latitude, longitude, and altitude. Those are our 3 translations to find out where that plane is. And then you have 3 more tudes. They're the attitudes, and those would be pitch, roll, and yaw. Well, on a part, we use our datum features to immobilize the part, partially or totally, so that we can inspect it. And so that's what I want to talk about today, is how do we immobilize the part? How can we do it with what's known as exact constraint? If you can fully immobilize your part on the 3 axes, so you've taken away the X, Y, and Z translations, and the 3 rotations about those axes, that is known as exact constraint. Many times when I'll look at a design, I'll say, what locates this part on the mating part? And people will tell me that it's going to hit here, 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 and here. And I say, whoa, 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 wait a minute. You're expecting it to hit in too many places. That's not going to happen. You're trying to get over constraint. And, if you're dealing with a real flexible part, over constraint isn't always a bad thing. But on the more rigid parts, if you try to get over constraint, you might end up pulling the machine apart. I know there was a company that was building copiers, and they had over constraint when they ended up tightening up the bolts that held the main engine, they called it, in the copier. They were actually trying to rip the thing apart. So if we can constrain or arrest all of these degrees of freedom, then we get this thing called exact constraint. Now, when I look for guidance in the Y14.5 standard, I look under the section with datums. And the standard doesn't have a lot of application, but in this section they tell us how we should pick datum features. But I get a little confused by the guidance that they give there. The standard says that functional relationships to the tolerance features and the requirements of the design should be taken into consideration. Well, that's cool. I'm good with that. But then it says to ensure proper assembly, corresponding interfacing features of mating parts should be selected as datum features. Well, there's a whole lot of parts that mate that shouldn't have datum features where they mate. You may have some frame, and then you have a lot of other little components or parts that mount to it. You don't necessarily have to create datum reference frameworks where each one of those little parts mounts. I know there's some companies that do, but every time you set up a new datum reference frame, it is a new setup and inspection. Every inspection has error or uncertainty of measurement. So sometimes there's a better way. The standard goes on to say that you should be able to get to your datum features. They have to be accessible. I'd agree with that. They have to be of sufficient size to permit their use. Now, what is their use? Well, their use is to constrain some degrees of freedom. If they're too small, they can't do a good job of it. In the fundamentals class, I'll often hold up a quarter, and I'll hold it between my fingers and point out that the outside of the quarter is a cylinder, and a cylinder constrains 4 degrees of freedom. But if I try to use that cylinder as my primary datum feature, it's too short to do a good job of 2 of those degrees of freedom. I won't get reproducible results. So that quarter isn't thick enough or of, I'll say, sufficient size to permit its use as, say, a primary datum feature. It's a dandy secondary datum feature, but wouldn't make a good primary datum features. Also, datum features must be readily discernible. When you have symmetrical type parts, you might have to put a chamfer someplace, or I know one company actually stamped the letter of the datum feature right on the part, so everybody set it up the same way. Well, I'd like to show you a few case studies and how things were changed a little bit to do a better job. This is a case study of a cover. This cover is used to mount onto a casting, and there's flammable liquid underneath the cover in this area and this area. So they had this position tolerance on the 8 holes, and it was a die-cast part. But they wanted the cover to align using these screws. So they had the 8 screws going in there in assembly, and they had a dedicated machine to drill and ream these holes. Now, the problem down at assembly is they had to start all 8 holes and then go back and tighten them. If they drove a screw right away, the cover might have been shifted off so you couldn't get some other screw in there. So here's that instruction, once again, that we find in that manual. Do not tighten until fully assembled, then go back and tighten. So the holes were drilled and reamed on a dedicated machine. My goal was to get rid of that dedicated machine. They wanted the holes to do a good job of locating the cover. And I asked the designer, which of the holes here does the locating of the cover? And he said all of them. That's why we drill them and ream them. Now, if you're worried about a shear load, if this was a brake pad and you had 6 or 8 rivets and you're worried about shear load, yeah, you'd have to really hold the location tight so they all carry the shear load at the same time. But many times, as with this cover, those screws were just there to clamp once the thing was aligned. Now, keep in mind, if I put position tolerance on those holes, from part to part to part, those holes are moving all over the place. If I ask really what holes are going to locate this cover, it's whichever 2 are the farthest out of location. They're the ones that will hit the screws first, and then hopefully the rest will clear. If I were to ask you, which of the holes on this cover would you like to use to locate it, what would you tell me?
Probably the 2 horizontal, farthest left, farthest right.
Yeah, the ones that are the farthest away is usually what people say. But even if I put position tolerance on those 2 holes, they're moving around. And so I have to open up these holes bigger than I'd like to because of the position tolerance in order to make sure I can get the screws through there. So I talked to tooling, and I asked them how well they could hold the size of the holes. And I also asked them a little bit about other things like orientation of the holes. What I like to say is when you're selecting your datum features, you should select the features that in the part's function constrain the most degrees of freedom. If you do this, you'll end up with less variation in your assembly, and so that's the approach I took on this cover. Something to keep in mind is I don't care what process you study. If you look at the 4 major characteristics, location, orientation, size, and form, the one that requires the most tolerance is location. The one that requires the least tolerance in your manufacturing process is form. Let's think about it for a machining process, for instance. The form comes mainly from your speeds and feeds, perhaps in like a milling operation. When you go to the size, that often depends on the size of your tool and your speeds and feeds. So you're getting a little more involved there. By the time you get to orientation, that's how well you squared up the column on your mill and your bed and the travel and all that. So you're getting into that, and you're also getting into the speeds and feeds in the tool. It's all part of that. And when we talk about where a feature is that you're creating in that process, now you're into all the dynamics of the machine. So study after study tells us the most difficult thing to control in a process is location, followed by orientation, then size and form. So keeping this in mind, if I can somehow take position out of the equation when I'm locating the part using these features, I could use tighter tolerances for orientation and size. So what I did is I recommended that they make one of the holes a smaller hole close to the size of the screw, and a slot at this end. Now the length of the slot was calculated so it never peeks out from underneath the head, so the customer won't know there's a slot there. But what this did is it takes that variation in position out of the equation. Instead of both holes trying to locate this part, only the one on the left is going to control the location. And then if I were to ask you, what is the relationship of this hole to the plane established by datum feature A, what would you tell me? Is it location, orientation, size, or form? Michael, you were right. It's hard to get response when you're doing a webinar.
Yes. Ask the question again, Don.
Sure.
Orientation.
There it is, orientation. My question was, what is the relationship that I need to control between this hole and the plane established by A? And the answer isn't where it is, because it's going to become my datum feature B. It's going to become my origin of measurement. So the relationship is just orientation, in this case, perpendicularity. And so I can hold that perpendicularity very tight and still not add cost to the part. You kind of get it for free with your process. And then if I come over here to C, well, the relationship of C, it's going to be this width here, is perpendicularity to A, or to the plane A establishes, and a little bit of position to B. So the correct call-out would be position, because I don't want the slot running off at some angle here. But it's mainly orientation that I'm getting. So once again, I can tighten up that tolerance a bit. So here you see in both cases I'm using the 0 at max material condition. So both of these tolerances become dependent on what I actually make the size. And maybe I'll pause for just a moment to make sure everybody's comfortable with using 0 at M. Is there any question there?
My manufacturing engineer doesn't like that.
The manufacturing engineer doesn't?
No, he thinks he's got to have some sort of number in there. Yeah, that's using a laser cutting a piece of steel. He shouldn't. I don't think he should have that issue, but he thinks he does.
Yeah. First I tell him there is a number, it's 0.
Mm-hmm.
They don't like that answer. But I guess what I'd show them is maybe a dynamic tolerancing diagram to show what's really going on, because the size of this hole can go from 6.2 to 6.3. And the only time that you'd have to hold at 0 is if your, pardon the expression, is dumb enough to make it 0.2. Because as I make this hole larger, I get perpendicularity tolerance. So out here at 6.3, I'm getting 0.1 millimeters of perpendicularity tolerance. So if he's shooting for something in the middle here, he's getting a couple of thousandths perpendicularity. And by the way, in this case, you notice this isn't very thick. And it's a casting. They're going to draw that pin. It's going to be pretty darn perpendicular. So they probably won't have any trouble holding that perpendicularity. So, you know, when people see 0, I say, no. It's kind of like when I go to the doctor and I have this rotator cuff problem, and I raise my arm and I say, Doc, it hurts when I do this, and he says, don't do it. Well, you have to read the whole sentence here. It's going to hurt you if you make it at 6.2 at M, but if you don't, you start getting a bunch of tolerance. And I don't know if saying it that way will help at all with your process engineer, but I run into it everywhere I go. I know what you're saying. So if I do this, now I've done a much better job of locating this cover using these 2 screws. And as far as this 8.25, that's another feature of size, the length of that slot, so I'm going to have position on it to ABC. And on these holes, I can open these holes up. All they're doing is clamping now. They're not doing any locating. I can give them a boatload of tolerance. And if your process engineer had trouble with these 0s, he'll really hate that one right there. But what it's giving him, if he shoots for 8 and he puts the holes in at 8, he's getting 1.5 millimeters. What's that, about 60 thousandths position tolerance, even though it says 0 here. So he could probably put those holes in with his Black & Decker hand drill. So given a whole boatload of tolerance, and the way I came up with the size was I made sure that the holes never peek out from underneath the bolt. They're just clamping. It's not that critical. So any question about what was done here to get better alignment of the part? I will say sometimes people say, oh, a slot costs more. Well, if it's in a CNC machining center, it's called a G01 code, which is a linear move to create a slot. And in sheet metal, in castings, in molded parts, it's free. You're not going to pay extra at all. So at the end, what we accomplished was we were able to use these parts as cast. I got rid of that dedicated drilling and reaming machine, and we're actually locating the part better as cast. Tremendous savings in cost on the part. Also, the alignment of the cover was greatly improved, and assembly was able to put the screw into datum feature B first, then into datum feature C, and then we just came out with some order of putting the screws in that made sense, but as soon as they put the screws in, they could drive them home. No more leaving everything loose and then going back and driving the screws. Any question or comment?
No, it makes absolute sense.
Sorry?
No, I was saying no, it makes absolute sense.
Oh, good. Okay. Now, we've got a company up here in the Rochester area that makes copiers. I'll just call them Company X. But what I found when I started working with them is this is their culture. When they're using stamped parts and molded plastic parts and cast parts, wherever they can, they try to use a couple of semi-perfs. So these are perforated but not all the way through, so you get a little boss on the bottom of this sheet metal part going into a hole in a slot. And then if you're using a screw, it's just there to hold it in place, one screw to clamp. I go to a lot of places where what they would do is they'd have two holes here and two screws trying to hold this thing on there, and you wouldn't locate it as well. So let me give you an example of another example where I've used this. This is a blower motor. Well, it's not the whole motor. I don't have the shaft in here, but this is the housing and this is the end cap. And originally, they held it together with these toy tabs. So if you see the little tabs right there, they get bent over to hold the two parts together. And they were also using those toy tabs to locate these two parts. So the end cap is over here on the right, has little toy tabs in it, you can see. And then the housing had these square holes that the toy tabs went into. And once again, because of positional variation, they didn't do a great job of aligning. And I said to them, you know, what features align the cover to the housing? And they said, well, these 8 tabs. And I'm going, oh my goodness, okay. Now, the problem wasn't that it couldn't go together and work. It did go together, but you'd get some shift in this part relative to that. And it still worked because the bearings that they had down here and down there that the armature shaft rode on were self-aligning. They were pretty clever about that. So these were free to rock around to line up to the shaft. The trouble was the misalignment could sometimes be so great that you didn't get a nice uniform air gap between the magnet and the armature. And if you don't have a uniform air gap, you don't get as much power out of this motor that you were looking for. So they really needed to align these parts better to one another. The solution was to add a couple of semi-perfs here, right in the existing tool, and to add a hole and a slot once again here. So they did a very accurate job of locating, and then the toy tabs were used, bent over to hold the whole thing together. Now I don't want to give the impression that this is the only way to do it with this hole and slot and semi-perfs. Here's a little scheme, and then I'll show you a place where we've used it. But I'm getting exact constraint once again. As we look at how these two parts go together, they mount on this surface right here. So that would be your primary datum feature for both parts where they come together, that interfacing mating surface. And I probably have a flatness on there. But then I ask the question, okay, now who takes away the most degrees of freedom? Sitting down on a plane takes away 3 of your degrees of freedom. Well, these little tabs going into these slots are taking away the up-down movement and also the rotation. I just kind of draw that in for you. So the little tabs are taking care of this movement and this rotation. So we've called out those two tabs as datum feature B. And I had to put position on them to keep the two tabs in line to one another. But by saying position with respect to A, also we're getting some perpendicularity between A and those tabs. Well, once I've done that, the only way that the cover can move on this is left-right. And so the outside of the tabs, I'll mark that up a little bit, this outside surface on the tabs is contacting the cover here and here. And so this width wants to be my tertiary datum feature, called it C. And I asked the question, what's its relationship back to A and B? Well, its relationship to A is perpendicularity, and its relationship to B is perpendicularity. So I put a perpendicularity on that. And once again, keep in mind, I can hold that perpendicularity tighter than I could a position tolerance. So I'm treating the outside of those two tabs as though it was one feature of size and using that as my third datum feature. Did the same thing on this cover. There's A, and I put flatness on it. And then B would be the two tabs, the width of the two tabs. That's taking away 2 degrees of freedom. And then C is taking away the one remaining degree of freedom. Now, this was kind of a simplified example to illustrate what's going on here. But if you took the brown bag, or if you looked at the brown bag on customizing your datum reference framework, you might remember this one. But this was a back for a cell phone. And the primary datum feature wants to be this little saddle shape here. And if I didn't customize the datum reference framework, the only degree of freedom that that little saddle shape wouldn't take away would be movement in and out of the screen in this view. Or up here in this view would be movement along the y-axis. However, it wouldn't do a very good job of stopping rotation. So I'm talking about this rotation. Because it's so shallow, it doesn't do a good job of stopping that rotation about the z-axis. You see your z-axis here, and in this view, z is coming out at you. That rotation is known as W when we label our degrees of freedom. So what the designers wanted to do is do a better job of stopping that rotation as well as stopping the movement in the y direction. So you'll notice they added some little tabs here. And those tabs, just like the ones we just saw in the last example, go down into a couple of slots in the mating part. And those tabs together, those two tabs, are datum feature B. So we have a position tolerance on those tabs with respect to A, and it also keeps them in line to each other. But what I had to do in this case is customize the datum reference framework, because A gets there first. A's trying to take away the W rotation. So what I did here is I said, well, A is going to take away U, V, X, and Z. You see that right here, but not W. Naturally, it would like to take away W, but I didn't include it. And then I'm telling you that B, those two tabs, are constraining W and the translation in the Y direction. So once again, we're ending up with exact constraint. And I know there's a lot here if you haven't seen customized datum reference frameworks, but happy to answer any question on this that anyone might have.
If I can go for Tuesday.
How would you simulate something like that on a CMM, Don?
What software do you have?
Yeah.
What you're going to have to do is have some pretty good software that can match up to the points that you pick. Something like, I'm not selling CMM software, okay, but a couple I'm familiar with are PCDMIS and Smart Profile from COTEM, they can do a pretty good job of simulating that. I'll tell you, when we did this, you notice that this has an antenna. There's the hole for the antenna. This was a while ago, and the CMM software wasn't there. And so what they did is they built two fixtures. So they EDM'd the shape of that saddle into this fixture you see down here in red. And then there's the little slots that the tabs will go into. So this fits down in here. And then they scanned the part to see how close it fit the CAD geometry. And there was restraint on it too, because this thing's pretty flexible. But they didn't have the software just to scan or pick a lot of points and then match it up to your CAD data at that time. But the software's out there now, but it requires post-processing. It's not something that happens automatically. Did I answer that question okay?
Yeah, I was just trying to think, how could you calculate B&M and what options are out there? We get a lot of reports where we have modifiers, and some of these guys on the reports, they just put the difference from, the actual B to the max and in this direction here. So it could actually, for B, it's a point-to-point, left and right, but if the pin is up or down, the hole's up or down, it'd be some weird triangulation of that. I guess you'd have to have a CMM. I don't know that you could do that just in a spreadsheet.
No, you couldn't. You really couldn't. Not very easily. We used to do things like this with paper gauging, although this would be a challenge with paper gauging. And what you're talking about there is that M on the datum feature, which is going to allow a little bit of datum shift up, down, and a little bit of rock. And you're right, a lot of people don't know how to deal with that, and so what they'll do is they'll measure the size of B, and then they will try to add that into the position tolerance as some sort of a bonus, and that's just flat out wrong, to do that. Because just because those little tabs get a little more narrow doesn't mean that the hole here for the antenna is going to be able to move up and down more. That just isn't going to happen. So real good point, but you've got to have the right software to do it. Not easy. But these are complex parts too. So, we can't do it with our old gauge pins and angle plates and a height gauge. So good point. Any other comments? Okay, I'll take you through a couple more case studies here. I don't know, I wasn't watching the time very well. How are we doing? Oh, we've got time for these. This is good. Hope everybody's got their sandwich there. This is they call it a wiper bridge. It goes onto a windshield wiper. You're all familiar with a windshield wiper arm. And there's a little spring clip that goes in here, and this little pin passes through these two holes. But what I want to talk about is how this wiper bridge gets attached to the frame of the windshield wiper. It's riveted in place. Notice, though, that you have to go through 4 bends to get from one end of this part to the other. Because of those 4 bends, they can open up and close, and they had a hard time controlling the distance between these holes. In fact, if they hadn't added a secondary operation, they'd had to open these holes up quite a bit to be able to get the rivets in there. The result is that this bridge can rotate quite a bit relative to the frame of the wiper, and what that does is it throws off the attack angle of the wiper blade on your windshield. So that's not a good thing. You get smudging and skittering, and you probably all know what I'm talking about there. So just imagine as these 4 bends on this open and close, you see I'm going to get large positional variation between these 2 holes. Another great candidate for a hole and a slot, and that's exactly what we did. If I just open up the holes, then I've got this problem going on, because I'd have to open up the holes to accommodate what I just showed you there with those 4 bends. So I can go to a secondary operation, and that's what they did till I got involved, is they'd make these up, then they'd punch the holes later, and they could hold the position tighter. with a secondary operation. Another thing they wanted to do was to open the holes up a bit, but they really couldn't. You know, with the rivet and the head of the rivet, they could open them up, but then it would give you that rotation problem. So the solution was make this hole close to the size of the rivet. This perpendicularity probably could have been left off because we're talking about a hole in sheet metal. You're never going to blow that. But to be complete, I've shown it here. No problem holding 0 on perpendicularity on this. And then the slot. So now as this opens and closes, it's not going to affect the rotation of this on the wiper. So we can do a much better job of aligning it. So we brought these both down close to the rivet size, the width of the slot in that hole. And it eliminated that secondary operation, saved them a bunch of money. Okay, here's another one. This is called a chimney, although it's kind of a reverse chimney. It goes on a gas cooktop stove, and the purpose of it is to get air down to your burner. They had 4 holes here, and those 4 holes were for 4 screws to hold it in place. Here's the redesign. In the redesign, we only have 1 hole for 1 screw because we created alignment features for exact constraint. So in the original design, here's your chimney again. This is what it looks like. It gets screwed here into the kind of the lower pan of your cooktop gas stove. And they had to leave the screws loose so they could kind of rock this thing around and get the screws into those holes when everything was assembled, and it was a chore for them to reach up in there and tighten these screws once it was assembled. By changing to this design, it was much, much easier to assemble. You just slide the part in place. These are your alignment features, and the 1 screw holds it there. So here you can kind of see what the assembly would look like. The result, we reduced the number of parts that saved money. With these alignment features, you didn't have to leave things loose and then fiddle-de-fool around later when you were tightening the screws. And then these alignment features became the datum features on the part. So I've got a little animation here to show you how this goes into the assembly. So you kind of slide down on there, and here's the screw holding it in place. So what's taking away the most degrees of freedom here is actually this irregular feature of size. It's not a regular feature of size because I don't have opposed points for this 0.8 millimeter dimension, but it's what we call an irregular feature of size. And it's actually 2 of them. There's one here and there's one there. So I can tie them together with a new symbol that we have in the 2009 standard, and that's called the continuous feature symbol, the CF. So now it's saying treat these 2 as though they were 1 feature. And that 1 feature is going to be my datum feature A. And that'll establish a plane that'll constrain 3 degrees of freedom. Then as I slide up into those notches, I'm going to contact here and there. And so those 2 surfaces want to serve as my secondary datum feature. And I have to control them, so I have a profile on those. 2x, there's 2 of them, and they become my secondary datum feature. Now you might wonder why there isn't a 2x up here on A. Well, if you use the CF symbol, you're saying it's continuous and you're not supposed to put the quantity. But here, since I'm using profile, I do have to say how many surfaces are involved with that profile. And then lastly, the only thing this can do once I have B, because B will take away up, down, and it'll also stop rotation, is I have movement left to right. And so the inside here makes contact with the sides of the slot. And so there's my tertiary datum feature C. And its relationship back to A and B is perpendicularity, so that's what I put on it. So now I can control the rest of the part to ABC because I've created a datum reference framework here with those features, those alignment features. And this is one of those reduced dimension drawings. It's saying go to your CAD model to get the dimensions. So you have to query it to find out what these other dimensions are. Then I have a general profile on it. and I've overridden that general profile with the size tolerance, with this profile, with this perpendicularity, and with this position up here on the hole for the screw. So I'm saying you can get a millimeter of tolerance on all these surfaces. However, kind of care where that screw is. And so I've given you a size and a position on it. So we start by making sure we have geometry whenever possible that'll do exact constraint, not over constraint, not under constraint, and there's lots of ways to do that. And then we make those features become our datum features for our geometric control. And that's what I meant by having the right geometry on your parts. So we've got about 15 minutes left. Are there any questions about anything I said, or do you want to share some experiences you've had? Anybody?
If you've got a pattern of holes that you really do want to use the whole pattern and not just, say, pick two of the holes like you did in the first example and turn one into a hole and one a slot, or use one as a hole, one as a slot. And then you want to establish that as your B and C, or your secondary and tertiary datum features. How do you then define the axes associated with that?
Okay, excellent question. A couple different answers I can give you on that. If I have two holes here, and I call one of them out as B, and the other is C, that's what you're saying? And A is maybe some mounting surface?
Yes.
Okay. Well, following datum precedence, if we said A, B, C, A is going to take away 3 degrees of freedom, that first plane. Then B establishes an axis. And the standard tells us that that axis is the intersection of two planes. If you think back to geometry class, when two planes intersect, their intersection forms a line. Well, in this case, I've got a line here, an axis, and that's the intersection of two planes. But I don't know how to orient them until I get C. So with C, one of the planes passes through C, and really you're hopefully just using kind of the top and bottom of C to orient that plane. And then the other plane is at right angles to that plane. So here's your 0, 0, 0 origin of measurement if you do it that way.
Now, what if you had... Oh,
go ahead.
Well, what if you had a pattern of 6 holes, and you wanted to use all 6 of them to establish your secondary and tertiary datums?
Okay. So it's 6x, and I'll have a size plus minus something or other.
Mm-hmm.
I have to position them to control where they are to, let's say, A.
Yes.
Right, to control their relationship to one another. And then you want to call them out as B. That's technically okay to do. A little warning, though. Let's say I then have this feature, and I want to control its position. And I say position to A, B. If I stop right there, B applies at what we now call a regardless of material boundary basis, which means I'm supposed to fill these holes somehow to trap the part, to take away the movement. The standard does not tell us how to do that. They're not all going to be exactly the same size. They're not all going to be in the exact position. So if you think about filling these 6 holes with a simulator and then letting those simulators expand on the basic locations, I might end up hitting here on this one and, oh, I don't know, there on that one, and there on that one, and the rest of them might not have expanded enough yet. They're still hanging there like that. But I don't know if that's the right way to do it. Do I keep expanding these other ones even though these have hit and can't expand anymore? The standard doesn't tell us. So my recommendation, you can do this, but my recommendation is that you do it on a maximum material boundary basis, because then I could build a hard gauge or soft gauge in a CMM software, and it would be at the virtual condition of those 6 holes. Now, if you do that, though, you're saying, I'm going to let it rock around a little bit on that simulator. But if you try to do this regardless of material boundary, you are on your own.
I'm with you.
Yeah, the mass standard doesn't tell us what to do, the gauging standard doesn't tell us what to do, and 14.5 doesn't either.
And to be honest, that's what led to the question. I knew that it was okay to do it, I just didn't know how to inspect it.
No, neither do I. If you want me to take a moment to call up a file, I have a file where I show 3 holes, and I talk about the various ways that you can expand into those with simulators, but I don't know which one is right.
I'm with you.
Where's the center axis on that? Don?
Yes.
Where's my datum reference frame on this situation? Is it clocked?
Well, am I? Are you going to let me have M there?
Yeah, I'll let you have that.
Okay. Well, in your gauge itself, you could put it anywhere. I'd be tempted to say that your origin is kind of right down through the middle here. But since everything in your gauge is basic, I guess if I wanted to, I could put it over here.
Okay.
In fact, there's words to that effect in the standard that say it could pretty much be at any of those centers. As long as it's all basic. So I hope that answered it. I don't like the answer, but
Don, question. This is Rob. We have a question from a gentleman, Tungten Ozdemir, who does not have a microphone and sent a question in basically referring back to the example on the cell phone cover.
Okay.
His question is, how would you define the same datum reference frame of the phone cover if you use 1994, the standards, 1994 version instead?
Wow, that's a great question, and I had to. Let me get back to that. Did I skip it? Hold on. That's exactly what I had to do because, like I pointed out, that phone has an antenna. You can see the antenna hole. And back in those days, we didn't have the opportunity to customize the datum reference framework. And I had to write a very, very long note down along the side of the drawing to explain what was going on. We added the axes, talked about the degrees of freedom, and it was like a paragraph out of the standard to explain how to set the part up. And I took that to the committee when we were talking about customized datum reference frameworks and said, look, here's an example where I need it. And I don't know if my note is adequate. You know, the English language doesn't serve us very well. So in 1994 standard, we did not have a way to customize the datum reference framework. You could not violate datum precedence until 2009 unless you did it in a note describing what you were doing. You can always add a note, right? In section 3 of the standard, we say if the symbols aren't adequate, write a note. So once again, not a good answer, but the best one I can give.
Very good. I appreciate that. Thank you.
Okay. Any other questions? All right. Well, we're near the end anyway. There's only about 8 minutes left. That's great. And what I would do is really encourage you to contact me. I'll put my email here. It's pretty easy. Just Don at the website. But I'm really appreciative of ideas for these brown bags. And for tips. I hope you're all reading the tips. I'm behind. I apologize, but I'm catching up. And so there will be a new tip coming out next week, and then they're going to be rapid fire after that. So Don at Tec-Ease.com is how you reach me for suggestions on tips, brown bags, or if you just have questions in general on geometric tolerancing. Anybody have anything at all they'd like to ask or say before we put an end to this?
I've got one question about the previous brown bag sessions, looking at them through the website.
Yeah.
I've been catching up since I've just joined the premium membership, which I do appreciate this benefit, by the way.
Okay.
And looking at the others, it seems like every 10 minutes it kicks you back out and you have to re-log in.
Oh, I wasn't aware of that.
I've tried it from 2 different computers and had the same experience, and so I was just curious if that's typical.
Does anybody else?
I get the same thing, sir.
You do?
Yeah, Don, I get the same thing. Yep.
All right, Rob.
Oh. I guess I'm taking an action item.
Yeah, yeah, we're going to get Tammy and Wendy on that. We'll get that straightened out. I was not aware of that problem, but we will fix it.
Thank you. So it wasn't by design anyway.
Oh, gosh, no.
Yeah, and if there's a timer on it, it should be, the half-life of that should be much longer. So are you saying that it systematically logs you out after 10 minutes?
Yes, at 10 minutes in, it quits playing and it puts you back over to the screen where you have to re-log in, and then you go and restart it and scroll over to the point where you left.
Okay,
That's how it works.
Very good. Thank you, gentlemen.
You have been at other sites where you'll get a little note that says that your link is timed out, and I'm guessing it's just a setting.
Yep.
And we weren't aware of that, but we will fix it. Thank you very much.
Well, we do appreciate the videos that you have up there, and I have found them to be very helpful.
Well, thank you. And they'll be even more helpful if you just let me know what you'd like a little help with. Okay, so don't hesitate to contact me. Great. Anything else? Okay, folks. Well, I hope you enjoyed this brown bag. I'm not sure what the next one will be, but we'll come up with a topic real soon and get it up there so that you can plan to attend. So take care. Have a really good weekend, and thanks for attending.
Thank you, Don.
Thank you, gentlemen. Take care.
Thank you very much.
Bye-bye.
Okay. Bye now.
Bye-bye.
That's a pretty cool feature.